Welcome, campers. This is the audio overlay for the PowerPoints for Module 1 and Introduction. Primarily what we're going to be talking about in this is how do you know what you're looking at? Because most of you have had experience as radiographers or nuclear medicine technologists or sonographers, and you really don't necessarily know what you're looking at when you look at some other modality. So one of the things that we're going to do is we're going to be looking at that. At what it is that we really see and how to make it do what we need it to do. Really, it's all about energy. And when we look at medical imaging, it's always about the transfer of energy, the absorption of energy, the reflection of energy, the changing of the amount of energy in some way, shape, or form. Whether that's with there's different types of energies, such as ionizing radiation, all that kind of stuff, and we'll talk about that in a moment. That is specific to that, but it's always basically down to about imaging and how we do that kind of stuff. So we always record the changes or lack of change of information, and then we display it on a monitor or on a sheet of film if we're doing it the old way, and that display then tells us something about the patient's body or about the pathologies they have. Now, when we talk about the energy sources, there are three primary energy sources that we use, and one is ionizing radiation, one is sound waves, and the third one is magnetism in conjunction with radio waves, but it's primarily what we're interested in there is the magnetism. So we're going to talk about those three energy sources, and we will also look at that. Now, there are 5 basic modalities that we're going to talk about very briefly in this presentation. One is radiography, which also includes radiation therapy imaging, such as CT stims and port films and stuff like that. And that all uses ionizing radiation. We have CT scans, and that uses ionizing radiation with computer reconstruction. We have MRI, or magnetic resonance imaging, and that uses magnets, very strong magnets, and radio pulses and the computer reconstruction. We also have sonography, which uses sound waves and the echoes of the sound waves. And then finally, we have nuclear medicine, which uses ionizing radiation, but instead of it coming from an external source, it comes in from a radioactive material that's inside the patient. When we talk about ionizing radiation, there are 2 basic sources of ionizing radiation. And one is X-ray and therapy machines. And you may be wondering why I might be adding therapy machines on here. I'll explain in just a moment. But on both of those, they're both external to the patient, so the radiation source is outside the patient. And what we do is we measure how much of the radiation makes it through the patient. And this includes radiographs, CT scans, treatment plan verifications, fluoroscopy, and all that kind of stuff. The reason I add therapy machines is because in recent years, therapy machines have gotten quite sophisticated, would be one way to describe it, but they add in such things as digital imaging plates and digital, not digital, but CT rotational scan capabilities on actual therapy machines so that you can do the day-to-day image-guided therapy. The second source is nuclear medicine, where we use radioactive materials, and we put those radioactive materials inside the body. So we inject them, inhale them, or those are the 2 most common ways. And what we do is we measure how much radioactive material is concentrated in given areas, and that tells us a lot about the physiology of the body. When we talk about sound waves, we're really talking about sonography, of course, and it's very similar to sonar. So it's where the sound is sent out and the echoes are recorded. So if you listen to the old movies where they're in the submarines and they say, ping and see what it is, and they go bing, dong, that kind of stuff, that's sonar. And we do something very similar to that in ultrasound. It's just the sound waves are extremely high pitched. We can't hear them, that's why they're called ultrasound. And we put out lots of them per second instead of just one every now and then. And the strength and the time it takes to return the echo tells us an awful lot about the structure that it's being passed through or didn't pass through, as the case may be. And sometimes we're able to even tell things about the moving parts inside the body, such as blood flow or heart valves and things like that. So that's how we use sound waves. With magnetism and RF pulses, and what we're dealing with is that in MRI, we put the body inside of a very strong magnet. To give you an idea how strong the magnet is, it's somewhere between 20 and 40,000 times stronger than the magnetic field of the Earth. And when we put a body in a magnetic field like that, the water molecules inside the body line up because they get magnetized. Then we send a little radio frequency or RF burst through the body, and that causes those atoms to change the way that they're lined up. And when they line up and then they're moved and then they re-line up, they give off a little tiny radio signal themselves, and we actually listen to that radio signal. And based on that and collecting that radio signal from lots of different directions, we're able to build images in MRI. In radiography, what we're looking at is essentially a radiograph as an X-ray shadow image. And in order to do a radiograph, we have ionizing radiation. It passes through the body, and different structures absorb different amounts. Now, what determines how much is absorbed is the thickness of the part. So thick parts absorb more than thin parts, and also what the parts are made of. Bone absorbs more than the lungs, as an example. And the resulting differences in the structure give us this shadow that we look at. What we typically see is that very low physiologically dense areas such as lungs and gas absorb very little radiation, and consequently most of the radiation gets to the image receptor, or the IR. When we talk about the IR response, lots of radiation hitting it, it shows up on the image as a white area, a dark area. Is that backwards? A high physiological area such as bone or contrast media or stones, that absorbs a lot of the radiation, so very little of it gets to the IR. Because very little of it gets to the IR on the image, that ends up being a very white area. When we talk about the radiographic image, what we find is that the more the radiation that reaches the IR, the blacker it is. So when we have an area such as air, absorbs very little, once it reaches air, it's black. When we have very little radiation reaching the IR, the area is white. So there we have bone and contrast absorbing the radiation. And then we have, those are the two experiences. In between, we have all kinds of varying shades of gray that occur because of different amounts of radiation that are indeed absorbed. We call that whole process differential absorption. And because of the differential absorption associated with body parts, we get a pattern of blacks, grays, and whites that represent the anatomy. And this pattern is seen as representing the pathology or the anatomy of the patient. What we have right here is we have an example of a radiographic image. And what I want you to notice is that right here we have a very dark area because there was actually almost nothing to absorb the radiation, and it struck the IR and is black. Down in here we have a white area, so the abdomen absorbed most of the radiation and very little of it reached the IR, and it's white. And then here we have the soft tissue in the neck and the chest. This is a very light gray, and this is a very dark gray. And when we do that, we see that that's because this absorbed a fair amount of the radiation, this absorbed some of the radiation. So we get all these very densities on here that we see. When we look at radiographic pathology, almost all pathological changes change the absorption characteristics of the part of the body. Some pathologies add density to the body. A good example of that is pneumonia or cancers that can add fluid or solid masses to the lungs. Some types, we call those additive pathologies. We also have subtractive pathologies or low-density pathologies that take away physiological density, and arthritis is an example of that, emphysema is an example of that, certain types of bone conditions are examples of that. And then we have other injuries or pathologies that change the contours of the structure. In other words, it doesn't look normal. Here we have an example of each of those three. This first one right here, what we find is this is a fracture. This is a bad fracture. This is a femur, and it must hurt immensely. But you'll see that the pattern should be that we have a nice edge that should go all the way up there like this, nice and smooth, and it's been disrupted. Therefore, we can see it. Here we have a cancer that has added pathology, and here we have a type of pathological process where the bone is being demineralized and eaten away. It's actually something that's called a rat bite sign. So those are the types of things that we find with radiographs. This is the end of the first audio. The second audio will continue with CT scan.